So, if Newton's universal law of gravity says that everything's attracted to each other along the line that connects the two of those, an interesting question then is, well, why hasn't the moon, or those satellites that we send up into space that we can actually use things like cell phones and watch TV and do things like that, why have they not collided with, say, the Earth yet? So let's say here's the Earth. We know that this thing is feeling now a gravitational force in this direction, so this is f of g. So we know that this thing then has to feel an acceleration then towards the Earth, and since the Earth is much, much more massive than, say, the satellite or the moon in this case, I'm just going to call this randomly m. Let's call this mass of the Earth for now. Then this guy is going to accelerate downward, so this one's going to be doing most of the motion. This one's not, because the acceleration of the Earth is going to be pretty much ridiculously small. Why hasn't the moon or the satellites collapsed directly into us? Well, the answer to this is they're moving. So basically, the moon or the satellite all have a tangential velocity, which is off in this direction. Right? So basically what's happening is, yes, this thing is actually falling towards the Earth. So as this guy is falling towards the Earth, but due to its tangential velocity, as it falls, it's actually also being carried in this direction. So by the time it has fallen this amount in this direction, it's also been carried this amount in this direction, which means its final location is going to be something like here. So what's actually happening is the satellites or the moon are actually free falling in towards the center of the Earth, but due to that tangential velocity as it falls in, it's also carried to the side, which causes it to actually move in a circle. So this thing is actually going to end up moving with a circular path. Now, what does that mean? I'll find something to throw. Doesn't work. So what that means is if I have this pen, if I could actually throw this pen fast enough, say in this direction, what would happen is as it's moving, it would actually be falling, but since it's falling it's moving so fast, by the amount of time it has fallen, it's also fallen the same amount at which the Earth itself is curving, meaning that this thing would actually be able to orbit the planets if I could throw it fast enough. So in this case, if I throw it in that direction, by the time it falls, it's going to follow the contour of the Earth, so meaning it's still free falling, it's still going towards the center of the Earth, but by the amount of time it takes for it to fall this distance, it has traveled a huge distance, which means it's actually going to end up going through the circular fashion. Now, of course, near the surface of the Earth, that's almost impossible for that to happen because we live in a fluid. We'll talk about fluids after for the next exam. But as we move through fluid, things that are trying to move through the fluid, as we talked about before, we have a drag force which is acting on it. That drag force causes it to slow down. So the faster I throw it, the faster that drag force causes it to slow down. So near the surface of the Earth, that wouldn't be able to be possible. But for the moon, which is outside of our atmosphere, again, as this thing radially falls in this direction, its tangential velocity carries it in this direction, causing it to actually move in a circle, which means that satellites and the moon end up going under uniform circular motion. Which means that there is a centripetal acceleration or radial acceleration towards the center. So a radial. So what this means then is if we call this direction, say again, our y direction, we can then say that the sum of the forces in the y direction are equal to the mass times the radial acceleration. But the only force in the radial direction is the gravitational force. So we have the gravitational force in this case is the centripetal force. So we can then ask, what is this tangential velocity which is going to cause this thing to move in an orbit of radius r? Well, we know here this is going to be the same thing as g times the mass of the Earth times the mass of the moon or the satellite, divided by the distance r squared, is then equal to the mass times, in this case, the tangential velocity squared, divided by the radius. Good. So this radius is the same as that one, so this one's going to cancel out from him. This mass is the same as this one, so it actually doesn't depend on it being the moon or a satellite. It's actually exactly the same thing. So this then gives me that the tangential velocity is going to be the square root of g times the mass of the Earth divided by the radius. So basically, what this says then is that the smaller the radius gets, the faster this thing is actually going to be moving around. So good. So this is then the velocity that this thing needs to make sure that it doesn't crash into the Earth. Now, of course, if the velocity changes, it's just going to move to a different location. But eventually what happens is there is stuff in space. There are, dust and other things that it's going to collide with that does cause it to slow down. So eventually these things will end up in spiraling, causing us, typically if it's a satellite, usually what it's going to do is it's going to burn up in the atmosphere. But ultimately what happens is the moon is actually spiraling toward the Earth. Basically the reason for that is because the Earth's rotation is actually slowing down due to high tides. So basically as the moon is pulling the water closer to it, that causes a backwards force onto the Earth as it's trying to rotate, which actually causes the Earth to rotate slower. As the Earth is rotating slower, that's actually causing the moon to start to move in. So eventually what will happen is that the moon will actually in-spiral and crash with the Earth, causing us all to die. And since the Earth is actually rotating slower, other things are happening too, that the Earth is actually losing its tangential velocity as well, causing it to in-spiral into the sun, which means that eventually we're going to crash in with the sun. So we'll all die. Or the sun at some stage will run out of its nuclear fuel. When it does that, it's going to turn into a red giant, which basically means that the size of the sun will actually blow up and it's going to become much bigger, and the Earth will actually get engulfed inside of the red giant in the sun. So again, we're all going to die. So the point is, at some stage, we're all going to die, whether we live forever or not. So anyway, so this is the tangential velocity that we need to actually make it through and stay in orbit. So good. So the last thing we want to talk about is then going to be Kepler's laws. So let's talk about Kepler's 3 laws. So Kepler's laws of planetary motion. So the story of Kepler actually goes back to a Danish nobleman by the name of Tycho Brahe, who actually, at night, he owned his own island. He actually had a telescope, and he would look up in the telescope and basically meticulously record the locations of all the planets and all the stars and everything that he saw. And he was world-renowned for his ability to take data. So basically how precise his data was and how meticulously he took it. During the day, he would actually test projectile motion, so the things that we did way back in chapter, 4. And the way he would test this was by shooting catapults at his cows. So his favorite targets were his cows. So he would try to kill his cows by shooting catapults at them to basically try to test and verify projectile motion. But anyways, so Tycho Brahe, he actually got a postdoc or a research assistant by the name of Johannes Kepler, and basically he paid him to basically look at the math because Brahe didn't want to do anything with the math. And then when he died, he left all of his data to Kepler, and then Kepler, without the use of a computer, basically without the use of anything, went through and he meticulously studied all of that meticulous data and then came up with the 3 laws of planetary motion. So let's look at Kepler's 3 laws of planetary motion. Now, what was also interesting about this was that Kepler didn't have access to Newton's universal law of gravity, so pretty much everything he said and what he wrote down, which turned out to be completely accurate, was based purely off of data and had nothing to do really with the universal law of gravity, which Newton actually used his universal law of gravity to prove pretty much everything that Kepler had said, and of course Kepler was actually absolutely correct. So here there are 3 laws. So what are the 3 laws? So the first law is what's known as the law of ellipses. So what the law of ellipses says is that all planets orbit around the sun in an elliptical fashion where the sun is at one focus and there's nothing at the other focus. So every ellipse has two foci, and the sun is at one of them, and there's nothing at the other one. And each planet, so this would be, say, the Earth, for example, orbits around the sun in an elliptical fashion. Now, each one has a difference, what's known as eccentricity, which is how much of an ellipse that it actually is, but each one does go through an elliptical fashion. Some are closer to a circle, some are much more pancaked out. But again, this is what we call the law of ellipses. So the law of ellipses, i.e. the first law, says that all planets rotate about the sun in an elliptical fashion where the sun is at one focus and there's nothing at the other focus. So this is the law of ellipses. The second law says, so here the second law says that if I looked at a particular time frame, so let's say delta t, and I look at the fact that my Earth was here, say at point A, and then moved to here at point B in this time frame, then this is going to sweep out an area here. Let's call that area A. Okay? So this is going to be area A going from A to B. Now if I look at another time frame, or actually the same time frame, but now the Earth, say, might start off here at point C, so that now it sweeps out from this radius. It's going to move to this distance d in the same amount of time of delta t. So now if I draw the radius out to d, this is also going to sweep out an area here, which is going to be the area going from C to D. Well, what the second law says is that this area here going from C to D is exactly the same as the area going from A to B. So as long as I'm looking at the same time frame of delta t, then the area from A to B must be equal to then the area going from C to D. So, second law then simply says that the amount of area which is swept out inside of each one of these wedges within the same amount of time frame is the same. So this means then that the areal velocity, which is then equal to the rate of change of area, is simply equal to a constant. That's what this thing says. This one's that's known as the areal velocity. So this guy's equal to a constant. So where does this come from? This actually comes from the fact that the Newton's universal law of gravity is a conservative force. And since it satisfies Newton's third law, this is also what we call a central force. So the fact that this thing only depends on the distance and the direction is in the radial direction, what this means then is there's actually no torque. There is no torque on the system. And since there's no torque, as we talked about, what this means then is that the angular momentum is conserved. And it turns out that this areal velocity then is actually proportional to the angular momentum, and since the angular momentum is a constant, i.e. it's conserved, then this areal velocity is also a constant. So this is the second law. So the second law again just basically says that in the same time frame, delta t, the amount of area which is swept out as this thing is going from one position to another position is exactly the same. The third law has to do with the law of periods. So the third law says that the square of the period, i.e. the amount of time it takes for the Earth here or any other planet to then circle about the Sun, is proportional to the radius cubed of its orbit. Now, that only mostly makes sense for circular orbits, because if it's a circular orbit, then the radius is constant. If this thing is an elliptical fashion, such as this, it's then usually defined in terms of what's known as A, which is equal to the semi-major axis. So in this case, if it's an elliptical, this would then just be equal to A cubed, which is then the semi-major axis. So all this means then is that the period squared is related to that radius, or that semi-major axis, cubed. Now this is also true for any object orbiting any other object. So in this case, we're specifically looking at planets which are orbiting the Sun, but this is also true for any other objects. For example, the moon orbiting the Earth. So in that case, the central body would be the Earth. The moon, then the period of the moon squared would be radius, or be proportional to the radius cubed, at which the Earth and the moon are separated by. Now, this is also true for other things too, say a supermassive black hole. So this is actually how we determine we have things like black holes. So basically what we do is we look out and we look at things like stars, and what we see is that the star might be orbiting around something that we can't see. So in this case, we can actually then measure the distance from the center of that unseen object to where that star is orbiting about, and then look at the period, and then from there we can determine the mass of that central body, and then from there that's how we know we actually have things like supermassive black holes in the center of galaxies, because we can't actually see these objects, but we can see the effects of them on other things around them. So this is a nice useful way in astronomy, for example, to always determine the mass of certain things that we can't actually see by seeing something else which is actually orbiting it. So we want to know now, what is that proportionality factor? So to do that, let's go back to, here's our Earth, or this is the Sun. So let's say, let's make this the Sun. So here's the Sun, and then here's the Earth. And the Earth rotates about the Sun in a nearly circular fashion. So we're going to pretend that that guy is circular. So in this case, this is my circular orbit. So this is my radius. Let's call that R. So good. So again, what we know is what? If this is a circle, this thing has a tangential velocity. It also has a radial acceleration towards the center. The only force acting on this guy is the gravitational force. So again, we're going to say that the sum of the forces, again, let's call that the y direction. This direction is equal to MAR. So in this case, this is then going to be equal to the gravitational force equal to MAR. Now, here we want specifically the period. So we're going to rewrite AR in terms of the period. So remember that goes as 4 times pi squared times the radius divided by the period squared. So the left-hand side is going to become G times the mass of the Sun in this case, times the mass of the Earth, it's going to take it as the mass, divided by that distance squared, is then equal to the mass times 4 pi squared times that radius, divided by the period squared. Okay, the mass of the Earth is the same, so let's go ahead and cancel that out. And then from here we want to solve for the period squared. So we have period squared then is equal to 4 pi squared divided by G times the mass of the Sun, all times the radius cubed. So in this case, our constant proportionality between the two is simply this guy, which goes as 4 times pi squared divided by G times the mass of the central body. So again, in this case, the mass of the central body is the Sun, so we would use the mass of the Sun. But again, this could have been the Earth with the Moon. In that case, this would have been the mass of the Moon. It could be a supermassive black hole with some star around it. In that case, it would be the mass of the supermassive black hole. So this constant proportionality always has exactly the same structure. It's always 4 pi squared divided by G times the mass, but that mass is always the mass specifically of the central body, which, as we said, doesn't have to be the Sun. It could be any object. So it could be the Sun, it could be the Earth, it could be Saturn, Jupiter, right? Whatever has moons or things going around it, or it could be a supermassive black hole. But again, these are Kepler's 3 laws. So the first 2 laws are more of ideas, not necessarily mathematical concepts. So as far as, say, something like a homework problem or something like an exam problem, you would only see the 3rd law, because this one is actually a mathematical expression. But again, as far as the exam is concerned, typically this would be something, either a subpart of a problem or some sort of short answer, quick calculation type problem. So that's it. That's everything for the exam. So next time I'll do probably a quick recap of everything. But as far as for now, we have everything that we need for the exam. So, yeah. So that's it.